So I'm hoping to put up the other assignments that are remaining for the semester. I'm hoping to put those up by the end of today so that you know in advance what's left, which isn't that much. You've got this, then a very simple assignment just to make sure you've got your a graph library working, and then you've got a final actual puzzle, which is a security question. Well, it's a graph problem that's dressed up like a security question. So I'm hoping to get that out to you. You've got a bit of a long due date on this one, a much longer than necessary due date on this one. But that is because, of course, that I'm going to assume you're not going to work next week, so it doesn't exist. This one is sorting. Let's see. Yeah, this is the older version. I put the newer version up online on Canvas. So on Canvas, yeah, sorry, did it on two different computers. So of course, here we go. So this assignment is due, I think, on the 30th, so last day of the month. And this one, I mentioned that you guys get a bit of flexibility. You can use any language you want for this one. This one is so if you want to do this in Java, just like we've been doing every other assignment, then great. That's what I'll be expecting. But if you want to do any other language, like Python or C or God help you PHP, then you can do it in any language you would like. I don't know. It's just that I picked something to pick on, and PHP was it. So there's only two types of languages: languages that people complain about and languages that nobody uses. So I did not come up with that quote. So anyway, this assignment you need to the first part of it is you implement 3 sorting algorithms: insertion sort, quick sort, and then one of these listed below. They're all in your textbook. Shell sort is one we didn't go over. It's very interesting because it's what its runtime is actually an unsolved problem, or at least it's one where basically you plug in some kind of factor, and that determines the runtime of it. And choosing something that's like a power of 2 as your factor, that ends up being go of n squared, but we can choose something better, and we think it's some kind of weird square root functionality of it, but we're not really sure. It's an unsolved problem as to how fast you can get shell sort to go. Merge sort, again, n log n time. Heap sort, n log n, and then there's tim sort, which is actually the default sorting algorithm that's used in a lot of sorting libraries these days. Like, it used to be quick sort or merge sort, and then they swapped it over to tim sort. So Java now implements tim sort internally. I think Python was the first one to use tim sort, but it's a very, very good programming language sorting algorithm that is a combination of insertion sort and merge sort, and it is pretty cool. It is also in the 3rd edition of the textbook, but it's not in the slides. So if you want to implement that, it's great, but it's worth more points if you do. So you're gonna make some minor changes to the sorting algorithms. You got to keep track of the number of comparisons. So anytime that an item is less than, or you're checking if 2 items are like less than or greater than, that's a comparison, right? You're checking which number is bigger, or doing a compare to station. That's a comparison. So keep track of how many times you do that. How many times you have to swap things, move things around, right? How many exchanges, and then the total runtime of the algorithm, right? Which is actually the least important thing, I feel, for measuring these, but it's still good to be able to test that. So implementing your insertion sort, that's 20 points. Your quick sort, 30 points, because that's a bit trickier. And then 20 points for your sorting algorithm of your choice. So that's 70 points just for implementing those and making minor changes to them, okay? The other points that you get are testing and collecting your data. So you want to test your algorithm on integers. A good test will be a lot of data points. And you want them to be fairly fairly different magnitudes. Like decent tests would have powers of 2s, but actually more than 5 data points. So 64, 128, 256, 512, 1024, you know, then 2048, and so on and so forth. So you get lots and lots and lots of data points, right? Get lots of data points. Okay. So output your data to a file, ideally, is kind of the point here. Well, I mean, you kind of need to output your data to a file because I don't want you to run this for me and I have to wait like 20 minutes for it to finish running, because ideally you're running something bigger. So instead, you need, well, this is the kind of thing where once you confirm it's working, you set up bigger sizes for it to work, and you hit the run button. You go and watch some TV or browse the internet or something, come back like in an hour, and it should, well, probably not an hour, but like in 5 to 20 minutes, and then it should be done with everything you need. So I recommend that you might want to try outputting your data into a CSV file, a .csv, and if you don't know what that is, a .csv stands for comma separated values. It is just a .txt file with a different extension. The only difference is that with a CSV file, anything that's reading it kind of assumes that there's commas separating all the data, right? So every line has data separated by commas, and and so it's just essentially a giant table. If you double click on a CSV file, it will basically immediately open in Excel or the equivalent on your computer. So it makes it very easy to import to Excel. Okay, so you're going to output this data. What is this data? That is, again, the number of comparisons, the number of exchanges, and the runtime. So, like, you might want to say insertion sort. This runtime, this size had this runtime, this extent, this runtime, this number of comparisons, and this number of exchanges for 64 items. Then for 128 items, do the same. Then for 256, do the same. All right. So the final bit is presenting your data, right? And this, right? Once you do the coding, you need to do this part basically by yourself, which is taking the data, and you need to present it to show that this works, so that we can you can show me which algorithm performs better, right? There's a bit of freedom here, but if you're collecting a lot of data, you should output your results to a file, right? And it should be in either a well-formatted table or graphing your data so that you can present it to me nicely, okay? So 15 points just for collecting the data if you do that correctly. But then another 15 is making sure you can present it in a way that I can actually digest the data and I don't have to ask you, what am I looking at? Because if I have to ask you what I'm looking at, then this point wasn't satisfied, right? Okay. So otherwise, this is fairly straightforward because the code, it exists basically everywhere. It's very rare for me to say the code is online, go and find it somewhere, or the code is in your book, copy it, right? But I mean, for this one, it's less about the algorithm and more about learning how to write to a file, how to present data, right, and how to collect data, right? There's kind of been a sub-theme that's been going on for the past couple of weeks of working with larger files, right, and working with programs that might take a bit longer to run, right, because there's just so much to process, right? So that's been kind of the theme there. So with that, I just want to go over, you'll have a quiz on sorting on Wednesday. And with that, I do want to go over the last sorting algorithm. It's not covered in the book. I was going to make a video of it, but I figure it's more fun to do here. Because it's a very weird sorting algorithm. In the amount of time that it takes this to work, right? On other sorting algorithms, the runtime we've had was O of n log n, right? Right, that's kind of the best time we had for sorting algorithms. But for this one, the runtime for this one is O of wn, where w is word size. So, for instance, if we're dealing with three-digit numbers, with numbers with 3 digits in them, then that's 3. If we're sorting things where the maximum word is, where the longest word is size 8, is length of 8, then w is 8. If the biggest word in the thing we're sorting is 12, then it's size 12. Now this sorting algorithm is called radix sort, R-A-D-I-X, and it's very interesting because unlike data and then swapping them as necessary, right? We're comparing one item to another. We're doing a bunch of comparisons, making sure something's less than, something's greater than, right? We're comparing for order. A radix sorts things without having to compare anything at all. So that makes it very interesting. It also makes it interesting because we're going to use a data structure to get radix sort done. We are going to use, I'm going to sort some 3-digit numbers. So let's start by coming up with 101, let's see, 221. Give me some more numbers, 3 digits. And if 775, 666, 999. Let's go with, I'm also going to put in a 2-digit number, 092. Merely because, but I'm going to pre-pad it with a 0, right, as you can see. I'm also going to put in 70. Again, I'm going to pre-pad it with a 0. And I'll put in, let's see, let's go with actually make that 95 and 76 and yeah, that should do it. Okay, there's enough things there. All right, so let's go ahead and see how this works. So the way this is going to work is that I'm dealing with 3-digit numbers, and these numbers have these are decimal numbers, meaning they have 10 possible different values. So I'm going to create 10 cubes. 3, 4, 5, 6, 7, 8, 9, 10. And I'm going to label them 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, so that I have a cube for each value. Okay? And radix sort works like this. I'm going to look at the least significant digit of each of these numbers, the least significant digit, so the ones place. And I'm going to just simply throw it into the matching cube. In other words, 101, its least significant digit is 1. So I'm going to throw it into the 1 cube, right? It ends with 1, so I'm throwing it into the 1 cube. 221, I throw that into the 1 cube as well because it ends with 1. 775, I throw that into the 5 cube because it ends with 5, right? 666 goes into the 6 cube. 999 goes into the 9 cube. 076 goes into the 6 cube because it ends with 6. Okay? So I put everything into the cube, right? And now I go through each cube and completely dequeue them. Okay? So 101, so we get 101, 221, 775, 666, 076, and 999. Okay? So dequeued everything. Okay? Now notice that with regard to the last digit, everything is sorted. With regard to, if we were just caring about the last digit, everything's sorted, right? 101, 221, 775, 666, 076, 999. Everything is sorted with regards to the last digit place. So now, what we do to continue the sorting algorithm is that we run this again, only we are going to run it on the second digit now. We're going to run it on the tens place, right? We did it on the ones place, we're going to do it on the tens place. So this time 101 goes into the 0 cube. 221 goes into the 2 cube this time rather than the 1 cube. 775 goes into the 7 cube. 666 goes into the 6 cube. 076 goes into the 6 cube, right? And it's going to go behind 775 because it's second in this list, so it's going in second. Okay, and then 999 goes into the 9 cube. Then we just simply go through this again and go and dequeue everything. 101, 221, 666, 775, 076, 999. Right? And if you notice, with regards to the tens place, the tens place, the ones place, now everything is sorted. Is sorted. So we've got 0, 1, 21, 66, 75, 76, 99. Right? So now for the third step. So if you naively guess that, well, now it makes sense to do it on the 100th place, you're exactly right. That's exactly what we're going to do. We're going to do it on the most significant digit now. So we throw 101 into 1. We throw 221 into 2. throw 666 into 6. We throw 775 into the 7 queue. We throw 076 into the 0's queue, which is why I pre-padded it with the 0, right? And then I throw 999 into the 9's queue. And now, right, notice, I'm not even going to have to dequeue it, but notice that everything is in order, right? Yes?
Why does the algorithm start with the least significant instead of the most significant?
I think if you do it this way, it's stable. Meaning that a stable is a property of sorting algorithms such that if I had two numbers that had exactly the same value, so let's say I had 005, let's call it A, and 005B, right? And A, such that A comes before B in our initial list. That in our output list, A will come before B. You can easily do this for the most significant digit. But I think there's not a guarantee that it's stable in that case. So if there's a way to do a stable algorithm, then I'm not going to do it that way. Insertion sort is stable. Not other algorithms aren't necessarily stable. I don't remember if quicksort is stable or merge sort, but that's just one of those things you care about it only when you really care about it. But you can do this from the most significant digit to the least significant digit, and it works just as well.
Is it not faster than
It's about, I would say it's the same because because the runtime for this again is O, W, N, where W is the word size, right? That was 3 in this case, and N because for each item we just throw it into a queue, right? We take each item and throw it into a queue, then we dequeue the item. So we do that we do that W times, where W is the number of digits we have, right? We had to do it. We did 3 times. We did that process 3 times for each number because each number had 3 digits. Now, mind you, in a computer, so why isn't this? So this seems pretty rad because that W is really small. So why don't we use this more? Well, in binary, so in a computer we don't really use it, but there is a very specific place where this has been used with great effect. But in a computer, right? This is, we're not dealing with 10-digit numbers. Sorry, with decimal numbers. We're dealing with binary numbers. So there's only 2 queues that we're using, and we're also using 32-bit numbers. So that means that that W is potentially, that's 32-bit. That's a 32-digit number. That's what 32-bit means. It's a 32-digit number. Okay? Because binary digit. Okay? So, and really, n log n, and in theory, an n log n algorithm would probably be running faster in that case. Unless, of course, comparisons are super expensive, in which case you don't have to really do any comparisons here. You just throw things into a queue. Right, so where has this been used? Let's go ahead and take a look. Radix sort, right? It's been used when you build an actual machine that needs to do sorting, right? Because especially early on when basically it's hard to build the mechanisms for comparing 2 items. But hey, if you want to just drop the right punch card into the right slot, right? Based on this algorithm and then run it on the next digit, that's pretty easy, right? You just simply take your items, then you simply grab them all and then throw them through the machine again, but it will operate on the next digit. So this was a machine made by, I think this was made by, IBM Card Sorter. Cards are fed into a hopper below the operator's chin and then sorted into one of the machine's 13 output baskets based on the data punched into one column on the cards. The crank near the input hopper is used to move the read head to the next column as the sort progresses. The rack in the back holds cards from previous sorting passes. Right, and let's go ahead and zoom in on that just to see what's going on there. But so you could use it, so this is great if you're building a physical machine that does sorting. Let's see. So 0, 1, 2, 3, so 0, 1, 2, 3, 4, 5, or sorry, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then it had 11 and 12 as well, and then it had different ranges for letters. Interesting. I don't know. I don't propose to be an expert in this machine, but this is what it was used. But it used radix sort to do its job. All right, and I also like it because in a data structures class, if there's an algorithm that uses data structures, I want to show it off, right? This is interesting because it uses a queue. It uses a lot of queues actually to do it. To do that, you don't necessarily have to use queues, but it's best to. Right, and it sometimes, yeah. But W is not a constant, so it's not an O of n time algorithm. It is O of Wn, and W is often bigger than that log n that we get when we do an n log n algorithm. Okay. So, and it also, you've got to use space for those queues as well. So it does end up, you've got, I've got all these numbers. I have to create a lot of queues for them. So, but it's a fairly straightforward algorithm. And I figure it's just a good thing that should be taught, because otherwise where are you going to get, where are you going to learn this stuff? It's not in your textbook. All right.